Welcome to graphing equations by using tables. On the first example here, we want to look at a table of values where you're always going to have to make up either some sample numbers for x or sample numbers in y. Traditionally, we would make up some x values. If you look at the table, we have an x value for 1. What we would do if we plugged in 1 to the equation that's given, we'd have 1 plus 2 that would give us 3. So our output for the y coordinate would be 3. We would do the same thing for 2. We plugged in 2 plus 2, we would get 4. So our output for y would be 4 when x was 2. If we plugged in 3, we would get 3 plus 2, which would be 5. And this concludes our first example. Just to take a look, these are some of the ways that we would actually look as we plug them in for us to show our work. Here's a graph. Once we had a table of values, what we would do in order to graph our answers is to take the coordinates, the input and output for each x, and graph them onto your coordinate plane, or in this case, the positive section of a coordinate plane. And the first one we want to plot is 1, 3. If we plot that, we would count over 1, and we would go up to 3, and we would place our point. We would do the same thing with 2 and 4. We would go over on the x-axis to a positive 2, then we would go up to a positive 4 and make our point. And then the last coordinate in our table is 3, 5. We would take that coordinate, we would go over to a positive 3, and we would go up to a positive 5. Once that is completed, what we would do at that point is to connect the points with a line. And we would now have graphed our equation y equals x plus 2 using the table method. Another example would be given an equation, and we plugged in 1 again. 3 times 1 is 3. 3 plus 1 is 4. And we would get 4. And again, we plugged in 2. 3 times 2 is 6. 6 plus 1 would give us 7. We plugged in 3. 3 times 3 is 9. 9 plus 1 is 10. Then again, we would plot each of those points. We'd go over 1. We would go up 4. Then we would go over 2 and go up 7. And then we would go over 3 and we would go up 10. And at that time, again, we would plot using a line that goes through each one of those, and then we would now have successfully graphed the equation y equals 3x plus 1. Looking at another set of tables, the same process, we would go through each one of these. This would ensure that we could have points to plot for each of these equations. In this case, if I had 5 times 4, I would get 20. 5 times 6, I would get 30. And 5 times 9, I get 45. And these 3 points will be plotted in order to graph the equation y equals 5x. Then we would go to another example table. Again, we just make up these values, 1, 3, and 10. Probably, if it was me, I probably would have used 0, 1, 2, just to have some easier numbers to do the math with. But 1 plus 5 would give us 6. 3 plus 5 would give us 8. And 10 plus 5 would give us 15. We go to the other equation, y equals 2x minus 2. Again, we make up some values. Well, I've made up 1. 2 times 1 is 2. 2 minus 2 is 0. Then 2 times 4 is 8. 8 minus 2 would be 6. 2 times 6 would be 12. 12 minus 2 would be 10. And again, we have the coordinates to graph for the equation y equals 2x minus 2. The last example is a negative 2 minus 1 will give us a negative 3. And a negative 1 minus 1 will give us a negative 2. And if I took 0 minus 1, it would give me a negative 1. And now I could graph these coordinates onto a graph, and it would be the graph of the equation y equals x minus 1. And this concludes our example of the 4 previous examples of equations. Now, here's another set of equations where they give us a bunch of numbers and we're trying to find the missing one within our table. Now, several opportunities we could use. Sometimes we can use, maybe there's a pattern or sequence. But one of the easiest methods is if 5 times what number would give us 60, or if we work backwards, 60 divided by 5 would make us be 12. And so that will be the missing coordinate, 12 and 60. Same as here. You know, what would we add to 5 to get 17? Or we could say 17 minus 5, and we do that, again, we would get 12. Here we had what number multiplied by 2 and subtracted, 2, will we get 18? Okay, or we could just say 18 plus 2 is 20, right? And then, so the 20 minus 2, excuse me, 2 times, say, 8, 16 minus 2, that wouldn't work. 2 times 10 is 20, 20 minus 2, so this should be 10. And on the last one, we got x minus 1. And we know that whatever minus 1 would equal to 7. Well, 7 plus 1 would be 8, so 8 would be our correct answer for that problem. Zero, 3, 6. They want to know which ones of these would be the easiest to answer. Well, we see the answers for this one. When we plugged in 0, we would get 4. If we plugged in 2, we would get 3 1/3. If we plugged in 4, we would get 2 2/3. Well, this would be more difficult to work with, whereas if we plugged in 0, 3, and 6, our answers would be a negative 4, negative 3, negative 2. These are much easier to graph. The reason why these x values worked out to be integers was because each one of these numbers are divisible by 3, which is going to give us an integer answer instead of a rational number. On the last one, we pick up more rational number answers, basically because 2 and 3 are not factors of each other, and neither are 1 and 3. So we would get answers that would be in fractional form. And that concludes our workshop for today.